In this video, we're going to talk about inheritance implementation issues. And the best source of notes for it is both the Scott Chapter 9 and my notes on implementation issues for inheritance. There's two principal issues that arise with doing implementation of inheritance in both C++ and Java. One has to do with the implementation of virtual methods, and the second has to do with object layout. We're going to start by talking about how you implement virtual methods. So with virtual methods, what we do, we have the amount of memory for an object. So with virtual methods, we have a block of memory associated with an object, and typically the first field in that object is going to point to something called a vtable that stands for virtual method table. So it's a pointer to a virtual method table, and now this virtual method table points to function implementations for each of the virtual methods. So for example, I might have a draw method, let's say a contains point method, maybe a toString method. So each of these locations points to the address of some code that we would execute when this method gets called. And this vtable does not contain the addresses of non-virtual methods because those can be inserted into the assembly code or machine code by the compiler at compile time. So it's only virtual methods that have to be looked at runtime depending on which object is currently assigned to a variable. So as an example, let's say that we have two classes, A and B is a subclass of A. And let's further assume that A defines two virtual methods, we'll call them X and Y, and let's say that B defines a third virtual method, Z. So any object of type A is going to have a vtable. So this is an object of type A vtable, which points to the implementations for X and for Y. Now, when we create a derived class or a subclass like B, it sets up its vtable so that the entries for A are in the same place. That is, the entry for X goes at the first location, the entry for Y goes at the second location. So this ensures that for both the superclass and all of its subclasses, the methods are in the same place in the vtable, so we always can jump to the same location. On top of that, we add a new method, Z, to B's vtable, representing that new method. So here we have methods for A and methods for B. As an example of what the compiler does, let's say that we have a variable, we'll call it myA, and let's do it in Java. So it's new, and we assign it an object of type B. Okay. And then we say myA dot Y. So what does the compiler do in order to compile this code? So the first thing it might do, and I'm going to use kind of abbreviated assembly code, is that it's going to load a register with the address of myA. So that's what we're doing here. We're assigning the address of myA to register 1. So at this point, we might have register 1, say, has the address of my A. Well, it's actually the address. What it has is the address of that instance of B. So we'll actually say the address of the B instance right here. That's what it contains. So it has a pointer. R1 has a pointer to that instance of B. So we'll say it has a pointer to this object right here. Now, it's going to load into register 2 the address of the virtual table. So this right here, the second statement is load vtable address, because that's at the first location in B. Then we want to call Y, and you can see that Y is at the second location, so we could load in the location of that, say, as R2 plus 4. We'll assume there are 4-point pointers, and that X would be at location 0, so Y would be at offset 4. And finally, we would say call R2, and that would call the function for Y. So right here, we're loading adder of Y. Here we call Y. So you can see that there are kind of an overhead right here of 2 additional steps that we would not need with a non-virtual method. With a non-virtual method, we still need this first step because we need the this pointer to point to the location of my A, or the instance of B in this case, and we would still need the call to a hard-coded address. So those 2 statements would still be there, but you can see in effect we've doubled the function overhead when we're using a virtual method. And this can be an issue when we have a lot of small methods, which is what object-oriented programming is all about. So virtual methods slow down a program. Okay, and why is that? Okay, well, the first reason is it doubles the overhead of calling a function, as we just saw. And if the functions were pretty large, that wouldn't be an issue. However, object-oriented programming tends to emphasize smaller functions that maybe only have a couple lines. In that case, that could significantly increase the overall cost of the function. So not only does it double the overhead of calling a function, but OO programming, object-oriented, that's what the OO stands for, often has small method bodies, and hence the doubling of the overhead could be significant. The second reason that it slows down a program is that C++ and Java, the compilers are often smart enough to inline methods that have only a couple lines. And inlining means that you replace the call to the function with the method's body. So for example, a classic example, let's say we have getLeft. Okay, and all it does is it returns left. So you might have something like right equals a.getLeft plus 10. Well, the compiler may very well replace that equal with something like equals a.left plus 10. compilers are smart enough to do that, provided they know at compile time what get left is going to be. With a virtual method, they don't know at compile time which version of get left is going to be used, and therefore they can't do the inlining. So the second reason that virtual methods slow down a program is they prevent a compiler from inlining methods. And that can significantly slow down a program because of the cost of doing the function calls. Now, just a couple side things that you may or may not have known about C++. So these are C++ side notes. So first of all, it's rare, but if you include a method body in a .h file, then most C++ compilers will automatically inline them. It's basically a directive to the compiler saying to inline these methods. 2, you can actually tell C++ to inline a method by declaring it as inline. So you could say inline int, say getLeft when you declare it, and then when C++ sees a method call to getLeft, it will do everything in its power to inline that method. Basically, you're telling the compiler, even if getLeft is fairly big, I still want it inlined in the code. So that takes care of the implementation of virtual methods. Second thing we want to talk about is object layout. And we've already started talking about object layout. We said that if there is any virtual methods, then we create a vtable pointer, or create a vtable and then place a pointer to it in the object. If there are no virtual methods, then there's no reason for a vtable and it's not created. After that typically comes the instance variables, and they start with the original superclass. So for B, we would first have A's instance variables, and then we would have B's instance variables. And this ensures that we can always find references to A's instance variables no matter what variable is actually there. So going back to our previous example with my A equals new B, and let's say we actually had a, let's say that A's fields included left, top, and color. And let's say B's maybe included label and font. So let's say that we had a reference like my A dot color equals some color, say color dot red. Okay, well, no matter what object my A points to, we can be guaranteed that color is going to be in the third location in the object's list of instance variables. So no matter what, let's say the vtable does exist here, we could basically know that the address for my color is roughly whatever my A is plus the get over the vtable. So let's say it's a 4 bytes pointers. So 4 bytes, this is for the vtable, so this gets us over the vtable to the beginning of the instance variables, and then it's in location 3, and since we use zero-based indexing, location 3 is really at index location 2, so we end up with the location or address being at MyA plus 12, which should make sense, right? 0, 4 is where left starts, 8 is where top starts, 12 is where color starts. So by always starting out with essentially the object layout for the superclass and then appending to that object's layout any instance variables for the subclass, we are able to ensure we always know how to get to the superclass's instance variables. And that same trick was used with the V table. So going back to the V table, we did the same thing. When we created B here, the way we created its V table was to take the V table from A and then append the virtual methods for B. That completes this video lecture.